In this video, we will be looking at complex numbers. So in all the problems we've been doing so far, if we're trying to solve, we've been getting real number answers. But if we want to think about the equation x squared equals -1, then to solve it, we would need to take the square root of both sides of the equation. So that would leave us with the square root of x squared, which is x, equals the square root of -1. But we don't take the square root of negative numbers because that's not a real number. So that's where we bring in complex numbers. Complex numbers are used to express non-real values. So complex numbers are written in the form a plus bi. So a is just a real number. Bi is going to be an imaginary number. So b is going to be some real number. I is labeled as the imaginary number. The imaginary number I is defined to be the square root of -1. So if you need to memorize something, it is that I is equal to the square root of -1. That means if I square both sides of this equation, we get I squared is equal to -1. Please, please, please make sure you have this. One thing that falls out from this is if a is a positive real number, then the square root of -a is equal to I times the square root of a. So the reason this occurs is because we can take the square root of -a and write it as the square root of -1 times the square root of a. But we just said that the square root of -1 is I. So we get I times the square root of a. What this means for us is that if we have a negative number under a square root, we can put an I in front of the square root, and that'll make the thing underneath the square root positive. So that'll be really helpful. We're going to start by just finding some complex numbers. So first up we have the square root of -25. So using that little trick we just learned, this can be I times the square root of 25. But the square root of 25 is 5. So this is I times 5, which we are going to write as 5i. That's all there is to it. For the square root of -50, we can write it as I times the square root of 50. But we have to remember how to simplify the square root of 50. So this is where having practice with the radical expressions is really helpful. So 50 is 5 times 10, and 10 is 5 times 2. So that means the square root of 50 is, we have a pair of 5s, so I can pull out a 5. The 2 doesn't pair up, so it stays under the radical. So that means I have I times 5 times the square root of 2, which we are going to write as 5i times the square root of 2. So in general, the I is going to come last. But if we have a square root attached to the I, we're going to put the square root last. The reason for that is if I were to write 5 times the square root of 2i, you would have to decide whether the I is supposed to be under the square root or not. And that's just not something we want to deal with. So we move the I in front of the square root so that it is very clear that the I is not under the radical. We can do operations on complex numbers just like we can on real numbers. We can add them, subtract them, multiply them, divide them. All of those operations still hold. And what's nice is what we know about polynomial expressions fits in really, really well here. So first I want to add 2 plus 5i plus -3 minus 6i. If I put my invisible ones out front and distribute them through, I'm looking at 2 plus 5i. 1 times -3 is a -3 minus 6i. I combine my like terms. 2 minus 3 is a -1. 5i minus 6i is a -1i. So we can write -1 minus 1i or more standard to write -1 minus I. We're always going to write the real number first, the part without the I, then we're going to write the term with the I. It's just standard, something we do. Next up we have 6 plus 2I minus -4 plus 3I. If I put my invisible ones out front and distribute them through, we have 6 minus 2I plus 4 minus 3I. I combine my like terms. 6 plus 4 is 10. -2I minus 3I is a -5I. 10 minus 5I. So we have our addition, we have our subtraction, next is multiplication. So we're going to start with 5I times 10 plus 3I. If I distribute through, 5I times 10 is 50I. 5I times 3I is a 15I squared. But I never want to see an I squared in your answer. Because we said I squared is equal to -1. So I'm going to write this as 50I plus 15 times -1, which is 50I minus 15. But remember, we want to put the real part first, which is the -15, and the part with the I, the positive 50I. We want to put that second. In this next one, we have 5 minus 7I times 8 plus 2I. We can distribute or FOIL this just like we would polynomials. 5 times 8 is 40. 5 times 2I is 10I. -7I times 8 is a -56I. And -7I times 2I is a -14I squared. So I need to combine some like terms. I have 40. 10I minus 56I is a -46I. Then we have -14, and I'm going to replace my I squared with a -1. So that's 40 minus 46I plus 14. And combining together, that gives me 54 minus 46I. Multiplying complex numbers is incredibly important, so we're going to do a couple more examples. First up, we're going to look at 5 minus 7I quantity squared. But when something is squared, that just means that it's multiplied by itself. So we have 5 minus 7I times 5 minus 7I. I'm going to multiply this one out like the last one, FOIL it if you will. 5 times 5 is 25. 5 times -7I is a -35I. -7I times 5 is a -35I as well. And -7I times -7I is a positive 49I squared. That gives us 25 minus 70I when I combine them, plus 49 times a -1, which is 25 minus 70I minus 49. 25 minus 49 is a -24, and we still have our minus 70I. So again, we're putting the real part first, the imaginary part second, and we don't want to see an I squared in our answer, because that's unnecessary. Next, we're going to look at, well, what if we multiply 5 minus 7I times 5 plus 7I? Let's try it. 5 times 5 is 25. 5 times 7I is a positive 35I. -7I times 5 is a -35I. And -7I times positive 7I is a -49I squared. So it gives us 25. The I terms cancel out because one's positive, one's negative. And then we have -49 times a -1. So we're looking at 25 plus 49. That's 74. That's a real number. So we just multiplied two complex numbers together and ended up getting a real number. So that's interesting. But these two complex numbers that we multiplied together, the 5 minus 7i and the 5 plus 7i, they are very special. They are called complex conjugates. And we actually have a slide based on complex conjugates. So complex conjugates take the form of a plus bi and a minus bi. Those two are complex conjugates of each other. And what happens when you multiply two complex conjugates by each other is that you get a real number in the end. That's going to be really, really helpful when we get to dividing complex numbers. So we're going to get some practice with just complex conjugates first. What it boils down to is change the sign on the term with the I. That's all there is to it. Don't overthink it. So if I want the complex conjugate of 3 plus 2i, change the sign on the I term, it's 3 minus 2i. That's it. If we have 4i, I can think of it as 0 plus 4i. So that would mean I have 0 minus 4i, which is just a negative 4i. So I really am still just changing the sign on the I term. And then the complex conjugate of negative 5i would be a positive 5i. So legitimately, only change the sign on the I term to get the complex conjugate. Now I mentioned these complex conjugates are important for dividing complex numbers. The reason that's true is because we don't want to leave any i's in the denominator. Kind of like how we rationalized denominators when we were working with radical expressions, how we wanted to make sure there were no square roots in the denominator. Same idea here, we just don't want any i's in the denominator. So what we're going to do is when we have a fraction with I in the denominator, we are going to multiply the numerator and the denominator by the complex conjugate of the denominator. So right now we have negative 1 plus 3i, so we're going to multiply by negative 1 minus 3i. But if we do it to the denominator, we also have to do it to the numerator so that the fraction stays equivalent. If I distribute through the parentheses, I'll have a negative 8i minus 24i squared over negative 1 times negative 1 is a positive 1 plus 3i minus 3i minus 9i squared. That gives us a negative 8i minus 24 times negative 1 over 1 minus 9 times negative 1, which is good because we wanted our i's to cancel out in the denominator. That way we don't have any imaginary numbers down there. So that's negative 8i plus 24 over 1 plus 9, which is negative 8i plus 24 over 10. But when I see this, I want to know if I can simplify it at all. The way I'm going to do that is by breaking it up like I did when we were dividing polynomial expressions. So we have a negative 8i over 10 plus 24 over 10. This first one is going to simplify into a negative 4i over 5 plus 12 over 5. But we want to put the real part first. So this is going to be 12 fifths minus 4i over 5. And just so you know, it is also possible to write this as 12 fifths minus 4 fifths I. The I can go out back. One more way to write it still would be 12 minus 4i over 5. Those are all acceptable answers. The second one, we're looking at 2 plus 5i over 2 minus I. Again, we want to multiply the numerator and denominator by the complex conjugate of the denominator. So we're going to be multiplying by 2 plus I this time. In the numerator, 2 times 2 is 4, 2 times I is 2I, 5I times 2 is 10I, and 5I times I is a 5I squared. In our denominator, we're going to have 4 plus 2I minus 2I minus I squared. So that gives us 4 plus 12I plus 5 times negative 1 over 4 minus a negative 1, which is 4 plus 12I minus 5 over 4 plus 1, which gives us negative 1 plus 12I over 5. If I break this up, that's a negative 1/5 plus 12/5 I. Neither of those reduce. So that's our answer. The very last thing we're going to do is look at multiplying complex numbers again, but we're going to multiply them in a slightly different form. So we have the square root of negative 5 times the square root of negative 15. Now, something that we've been taught from when we first learn radicals is that the square root of A times the square root of B is equal to the square root of A times B. The problem is this only works with real numbers. All right, so we have to be really, really careful, and I'll show you why. If I were to just multiply these, I'd get the square root of negative 5 times negative 15, which is the square root of a positive 5. This is going to be wrong. I'm going to show you why. The square root of negative 5, we know that's equal to I times the square root of 5, because that's just how complex numbers work. The square root of negative 15 is equal to I times the square root of positive 15. So if I take the square root of negative 5 times the square root of negative 15, that's going to be I times the square root of 5 times I times the square root of 15. If I reorganize this a little bit, this is I times I, which is I squared, times the square root of 5 times the square root of 15, which is negative 1 times the square root of 75. It is the opposite, legitimate mathematical opposite of what you might have expected. And that's just because this rule does not follow when we're working in complex numbers. It only works for real numbers. So that was wrong. This is the one we want. So this is going to be negative 1 times. We need to see if we can simplify the square root of 75. Well, 75 is 25 times 3, and 25 is 5 times 5. So that's going to be the square root of 75 is equal to 5 times the square root of 3. So we have negative 1 times 5 times the square root of 3, which is a negative 5 times the square root of 3. So if you are ever multiplying together complex numbers that are written in square root form, make sure you pull the i's out first. Otherwise, you will get the wrong answer.